Hello students, in the previous videos I discussed about the type 1, type 2 and type 3 problems. In this video I am going to explain type 4 problems. In this type, the procedure is very simple. Either they will be giving you u minus v, the sum or the difference of the real and imaginary parts will be given to us as a function of xy or r theta. It's a Cartesian or in the polar form it will be given. The procedure is we have to differentiate with respect to x and y both partially. Then we will be getting in terms of ux vx and also uy and vy. The second equation, which is having uy and then vy, needs to be replaced with x, that is by using the CR equations uy should be replaced with a minus vx and vy should be replaced with plus ux. After doing so, we will call that as equation number 2 and we will solve for ux and vx as the simultaneous equations. Once we get the values of ux and vx, we will substitute in the f dash of z, which is equal to ux plus ivx. Then put x as z and y as 0 in the case of Cartesian, whereas in the polar form we will put r is equal to z and theta is equal to 0, so that we will get f dash of z in the terms of z only. Then integrate, that gives us the required analytic function. Now let us go for this problem. So they have given u minus v is e power x into cos y minus sin y. We shall differentiate it with respect to x and y partially. When we differentiate this with respect to x, only this e power x will be differentiated because this cos y and sin y will be treated as constant when it is partially differentiated with respect to x. And derivative of e power x is e power x. Whereas when we differentiate this with respect to y, the derivative of cos y minus sin y will be differentiated. E power x will be treated as constant. So derivative of cos y is minus sin y, derivative of sin y is cos y. Now using the CR equations, we have uy is minus vx and vy is plus ux. So we need to substitute in the left hand side of the second equation, which is not named as second, but this is the equation. This equation we have to substitute. After substitution, we are getting minus vx minus ux is equal to e power x into minus sin y minus cos y. Taking the minus sign outside, we get ux plus vx is equal to e power x into sin y plus cos y. Now let us solve the first and second equation simultaneously for ux and vx. Now if I add the two equations, this sign term will get cancelled. We will get 2ux is equal to 2 e power x into cos y, that is ux is equal to e power x into sin y. When I subtract it, ux will be cancelled and also cos y term will be cancelled. We get minus 2vx is equal to minus 2 e power x into sin y. That gives us e power x into sin y. Later, we consider f dash of z as ux plus ivx. Then substitute the given, the ux and vx equations. Then take e to the power of x common. We get cos y plus I sin y or e to the power of iy. Then e power x plus iy and e power z. Also, we can do it as by taking x is equal to z and y is equal to 0. If we do that, we will be straight away getting e power z as it is because sin 0 is 0. So we get e power z and the integral of this e power z is again e power z plus the constant of integral. So we obtain the function f of z is equal to e power z plus constant. Next problem. If f of z is analytic with u plus iv, find f of z if u minus v is equal to x minus y times of x squared plus 4xy plus y square. Now we need to multiply this x minus y into x squared plus 4xy plus y square. Let me multiply and simplify here. X into x square is x cube plus 4x square y plus xy square. That is on multiplying x with these three terms. Next, minus y is multiplied with x square, this all the three terms. So we get it minus x square y minus 4xy square minus y cube. So x cube and y cube are single terms. It is written as it is, x cube minus y cube. Next, 4x square y minus 1x square y will become 3x square y. And xy square minus 4xy square will become 3xy square. This is how it is on simplification. Now differentiate this with respect to x. What do we get is 3x square plus 6xy minus 3y square. This is differentiated with respect to x and this y cube term will become 0. Next, let us differentiate this with respect to y. Then we get 3x squared minus 6xy minus 3y square. And as I told you, the second equation we need to replace with the CR equation. That is uy is minus vx and vy is ux. So we get the equation is minus vx minus ux is equal to 3x square minus 6xy minus 3y square. When I add the two equations, this as one equation and this as the other equation. Supposing if I add these two equations, what happens? We will be cancelling this ux and ux. We get 2 times of vx is equal to, I am adding, so 6xy cancels. We get thrice of 3x square. No, 3x square plus 3x square will be 6. 6x square minus 6y square. So it is 6 times of x squared minus y square. We get it. Or cancelling 2 on either side. So vx will be equal to 3 times of x squared minus y square. We get it. Similarly, when I subtract, that is vx is equal to, what is the vx we have got is 3 times of x squared minus y square. Next, when I subtract, what happens is ux, 2ux we will get it. 2ux, 3x square and 3x square cancels. 6xy and 6xy gets added. It will become 12xy and even 3y square gets cancelled. So what is my ux is 6xy. Right? So vx is 3 times of x squared minus y square and ux is 6xy and vx is this we are getting. Okay. So this is what we have done it. 6x square minus y square and minus of that we have got. Therefore it will be 3 times of y squared minus x square we have got it. There it was minus sign, I left it. So 2ux is 12xy, therefore ux is 6xy. Now let's consider f dash of z is equal to ux plus ivx. So we get 6xy plus I times of 3 into y square minus x square. When we put x is y, z and y is equal to 0, this real part will be totally 0 and even this y square part will also be 0. What we are getting is minus 3i z square. Now integrate this. We get minus I z cube because the integral of z square is nothing but z cube divided by 3. Already minus 3 is there. So this 3 and this 3 cancels. We get minus z cube. I is already a constant. Therefore, minus I z cube plus constant. This is what we are getting. Next problem. If f of z is analytic, show that dou square by dou x square plus dou square by dou y square into f of z the whole square is equal to 4 f dash z whole square. So let f of z is u plus iv be analytic. Then modulus of that will be equal to root of real square plus imaginary square, that is u square plus v square. And when we take square on both the sides, u square plus v square. So we can say that u square plus v square is equal to 5. We can say instead of c, it's a constant actually. We can say that as 5. So in order to prove that, now we have to prove that dou square by dou x square plus dou square by dou y square of 5 is equal to 4 times of mod f dash z whole square. That is, to prove that 5xx plus 5yy is equal to 4 times of mod f dash of z the whole square. Now let us consider phi. Phi is equal to u square plus v square and differentiate partially with respect to x. When I differentiate partially with respect to x, 2u into ux plus 2v into vx. Again, if you differentiate partially with respect to x, u into ux, we will be applying the uv rule. So we get 2 terms from this and 2 terms from vvx. uxx plus ux into, again derivative of u is once again ux. So it is ux square. Similarly, vvx plus vx square. This is called as a equation number 1. Similarly, when we differentiate partially with respect to y, we get 2 times of uyy plus uy square plus vvyy plus vy square. Call this as equation number 2. Now we need to add this 2 equations, that is equation number 1 and 2, and we have to prove the result. Add it. We will be getting twice of, group all the u terms separately, v terms separately, and remaining terms as it is. When I combine the u terms separately, we get uxx plus uyy, and v terms separately if I do vxx plus vyy, and remaining terms is ux square, vx square, uy square and vy square. Call this as equation number 3. And it is given that it is analytic, therefore u and v must be harmonic. So if u is harmonic, by harmonic property uxx plus uyy is 0, and if v is harmonic, vxx plus vyy is also 0. And we also have the CR equations vy is equal to ux and uy is equal to minus vx. Only the y parts will be replaced. So what happens? 2 times of u into 0 plus v into 0, because this uxx plus uyy and this one will be 0, that is replaced, and ux square and vx square is same, whereas uy will be replaced with minus vx and vy is replaced with ux. Now add the like terms, you will be getting 2ux square plus 2vx square, that gives 4 times of ux square plus vx square. Let's call this as equation number 4. So, but f dash of z is ux plus ivx, and we take the modulus, the real part square and imaginary part square, squaring on both the sides, f dash of z whole square is ux square plus vx square. So using that, in the right hand side of the equation 4, we have 5xx plus 5yy is equal to 4 times of f dash of z the whole square. This proves the result. Next one. If f of z is a regular function of z, show that dou by dou x of mod f of z the whole square plus dou by dou y of mod f of z the whole square is equal to mod f dash of z the whole square. So let's consider f of z is u plus iv be a regular function or an analytic function. Then mod of f of z is root of u square plus v square, that is 5. So we need to prove that dou phi by dou x, because mod of f of z is phi. So this f of z is replaced with phi. Therefore, we need to prove that dou phi by dou x whole square plus dou phi by dou y whole square is equal to mod of f dash of z the whole square. That is to prove that phi x square plus phi y square is equal to mod f dash z whole square, where phi is root of u square plus v square. Now squaring on both the sides, we get phi square is equal to u square plus v square. Now differentiate with respect to x partially, we get 2 phi x is equal to 2u ux plus 2v vx, and divide by 2, we get phi x is equal to u ux plus v vx. Similarly, when we differentiate partially with respect to y, we get 2 phi y is equal to 2u uy plus 2v vy. Again, dividing by 2, we get this equation. Let us call them as equation number 1 and 2. Now let's square them and add the equations 1 and 2. Then when we square it, it is phi square times of phi x square plus phi y square is equal to u ux plus v vx the whole square plus u uy plus v vy the whole square. By using the a plus b whole square formula, a square plus b square plus 2ab, here also the same thing we have. And we have f of z is analytic, so the CR equations must be satisfied. Wherever uy and vy is there, it will be replaced with minus vx and ux. Then what happens? U square ux square plus v square vx square plus 2uv into ux vx. That is, the first bracket remains the same because there is no vy or uy term. In the second bracket, u square uy square plus v square vy square, here we will be changing. That is, u square times of ux square plus vx square. That means when I group the first term of both the bracket, this term and this term. See, u square if I take, it is ux square plus uy square, where uy is replaced with vx. Similarly, when I take v square as common, vx square, and this will be vy square, that is ux. So again we are getting this. And these two terms which will be cancelled when I replace here with the vx. Uy is replaced with a minus vx. Therefore, this sign will become, see here, 2uv minus vx and ux. So, this will be cancelled with this. Okay. So, we are grouping the first term of these two, that is u square, and the second term of second term, so that v square terms we will be getting. Whereas the third term, it will be cancelled on replacing the CR equations. Now, so what do we get is, by taking the ux square plus vx square common, u square plus v square we get it. But we have phi square is u square plus v square. By using that in the right hand side, this phi square and phi square cancels. We get phi x square plus phi y square is equal to ux square plus vx square. But we have f dash of z is this. Therefore, mod of f dash of z the whole square is ux square plus vx square. That on replacing, we get phi x square plus phi y square is equal to mod of f dash of z the whole square. This proves the result. Thank you.